In this video, we're going to go over the formula version of Hess's law as well as combination questions. So the formula version of Hess's laws allows us to find the change in enthalpy of a chemical equation using the molar enthalpies of formation, which are in your data booklet on page 4 and 5. Okay, so these here are all of your values for molar enthalpies of formations for various compounds here on page 4 and 5 of your data booklet. Okay, so just as a note here, remember that the molar enthalpy of formation for elements, they're not going to be listed in your data booklet, but you should know that the molar enthalpy of formation for elements is going to be 0. So how you know when to use the formula version of Hess's law is basically when you're asked to find either change in enthalpy or molar enthalpy without a whole lot of information given. Okay? Usually they just give you a reaction and that's it. So the steps to solving problem using the formula version of Hess's law: step 1, you're going to need a balanced chemical equation. And then step 2, you're going to need to figure out the change in enthalpy for the reaction using this formula. So this formula right here. Okay. So it looks a little bit more scary than it actually is. So these symbols right here, they just mean that you're taking the sum of. So you're taking the sum of the moles of a product times the molar enthalpy of a product here. So let's write that. This just means the sum of. Okay. And so for these other pieces, so these pieces, you're going to find these numbers in your data booklet. So this comes from page 4 and 5 of your data booklet. Okay, and then last but not least, we have these moles. So they're just going to come from the coefficients from your balanced chemical equation. Okay, so the main idea behind the formula version of Hess's law is that we're taking the sum of the moles of our products times by the molar enthalpy of formation of our products and subtracting that with the sum of the moles of the reactants times by the molar enthalpy of formation of the reactants. So sometimes what I like to do just to remind myself is just to write products minus reactants, just to help myself remember that all of the information with the products comes first, all of the information relating to the reactants comes second. Okay, so how I'm going to be just writing out this equation when I'm doing questions here is just going to be change in enthalpy is equal to the sum of moles of the products times by molar enthalpy of formation of the products subtract by the sum of moles of reactants times by molar enthalpy of formation of the reactants. Okay, so this is usually how I write the formula that I've highlighted above in yellow here. Okay, and then step 3, we're going to use the change in enthalpy to determine what the question's asking for. So sometimes the question asks for change in enthalpy, other times the question asks for the molar enthalpy of a specific substance. So in our first example here, we're asked to find the molar enthalpy of combustion for ethane, which is C2H6. Okay, so molar enthalpy of combustion, so that's specifically for ethane. So we're finding molar enthalpy of combustion for ethane, C2H6. We don't know what that is. Okay, but first what we need to do is we need to find change in enthalpy using the formula version of Hess's law. And then from change in enthalpy, we can figure out the molar enthalpy of combustion using or dividing change in enthalpy by the moles of ethane here. So if you wanted the formula version of what I just said, what we're going to be doing is taking our change in enthalpy, dividing it by our moles to get the molar enthalpy of combustion of ethane. Okay, so if you wanted step 1, step 2, step 1, find change in enthalpy using Hess's law. Step 2, use this formula, and this moles is going to come from the coefficient in the balanced chemical equation. And it's going to be the moles of ethane that you use. Okay, so let's get started with this. So I'm going to first start out with just writing out my formula here. So sum of products minus reactants. So moles of the products times by molar enthalpy of formation of my products subtracted by the sum of moles of reactants times by molar enthalpy of formation of reactants. Okay, so before I get into this, I'm just going to write out my molar enthalpies of formation for each substance here. So let's start with ethane. Go to our data booklet. So this is on page 4, and I'm seeing ethane is right here. So it's negative 84.0, and our units are going to be kilojoules per mole. So I'm going to write this over here that my units are kilojoules per mole. So negative 84.0. So oxygen here, this is elemental oxygen. How I know it is because it's by itself, it's not in a compound. So this is just going to be 0. Because remember, the molar enthalpy of formation of any element is always 0. Okay, and that should be 0 kilojoules per mole there. Okay, now for carbon dioxide as a gas, let's look that up. So carbon dioxide is on page 4. It's right here, so negative 393.5. Okay, and then for water vapor, you have to be super careful with this because state matters here. So this is water as a gas. do not give the value for water as a liquid here because they are two different values. So to show you, I'm going to go to page 5. Okay, notice we have water as a liquid and water as a vapor. We need to choose water as a vapor here. Okay, so we're going to write negative 241.8. Okay, so what I'm going to do is I'm going to start off with my products here. And what I'm also going to do is I'm going to color code everything. So I'm just color coding this so that your eyes can track where each piece of information is coming from. Okay, so I've got, for my moles of carbon dioxide, I have 2 moles of carbon dioxide here. So I'm going to go 2 moles times by that negative 393.5 kilojoules per mole. Okay, how much? Yeah, I got lots of space here. Okay, so now on to my next product here. That's going to be the water. So because we're figuring out the sum of, we're going to be adding up these values. So I'm going to go plus, okay, 3 moles times by negative 241.8, and that's kilojoules per mole. And then we'll close the bracket because we finished dealing with all of our products here. Okay, now I'm going to move on to our reactants. So that's going to be ethane. Okay, so I got to go subtract. Now we're talking about our reactants. So our moles of ethane, there's just, whenever there's not a number or a coefficient written, you can assume that there's 1. And then molar enthalpy of formation for ethane is negative 84.0. Okay, so whatever you do, I recommend that you take the formula version of Hess's law very stepwise, because these, like what we write out for Hess's law can get very long, and if you put all of this in one line in your calculator, it's very easy to make mistakes and be wildly off with your answer. So I highly recommend you do it very stepwise. So how I'm going to do this is I'm going to figure out, okay, what is 2 times negative 393.5? What is 3 times negative 241.8? Okay, and then I can just do my reactants just as mental math there. Okay. All right. So 2 times negative 393.5, that's going to give us negative 787. Okay, and then 3 times negative 241. That's going to give us negative 725.4. Okay, and for my units, moles cancels out, so I'm left with kilojoules. Okay. And then what I have for the last part is just going to be negative 84.0 kilojoules. All right, so now what we can do at this stage here is we can figure out what all of this is equal to. Okay, so I'm going to go negative 787 minus 725.4, and then over here we have a negative times a negative. So negative times a negative is a positive, so I'm going to add that 84 to it. So my answer is going to be negative 1,428.4 kilojoules. Okay, so just as a reminder here, with SIGDIGs, so because what we did with our numbers, so with the amount of moles, those are not going to be used for SIGDIGs. What are going to be used for SIGDIGs are molar enthalpies of formation. Now, the reason why I'm not going to use my coefficients is just because they have infinite amount of SIGDIGs. So, like the coefficients could be 2, or they could be 2.0, or they could be 2.00, and keep on going and have an infinite amount of SIGDIGs. So that's why I'm not using the coefficients. Okay. Now for all of the molar enthalpies of formation here, since we ended up adding and subtracting them, okay, looking at my given numbers here, it looks like each of these just have one digit after the decimal. So as a refresher, for adding and subtracting SIGDIGs, you just go to whatever number has the least amount of digits after the decimal. So that's why I've just ended this with one digit after the decimal for my final answer for this section of solving this question. Okay, so now that we have change in enthalpy, okay, remember that this number represents the energy given off by this reaction. So it represents the whole reaction. It does not talk about a specific substance. Okay, so that's why I said in my steps, so step 1, use or find change in enthalpy using Hess's law, and then step 2, we need to take that change in enthalpy and divide it by the moles of our substance in order to get the molar enthalpy of combustion for our substance. Okay, so this is step 1 complete. Step 2, so maybe I'll write step 1 up here. Step 2, so molar enthalpy of combustion for ethane. I'm going to take that negative 1428.4 kilojoules and divide it by, we only had 1 mole of ethane. So even though this isn't going to change our value, I still want to see your work for this because I need to see that you understand that change in enthalpy and molar enthalpy of a substance are two different things. Okay, so this is the molar enthalpy of combustion of ethane specifically. Okay, now if you're wondering why our answer here is different than the number that we have on page 4 of our data booklet here, so I'll find ethane again. Okay, so this number for ethane was negative 84, whereas our our other number was negative 1,428.4. Okay, so the reason why there are two different values here is because the number in your data booklet, that is the molar enthalpy for formation. So it's specifically talking about the formation reaction of ethane, whereas the value that we calculated here is specifically talking about the amount of energy given off per mole of ethane when ethane is being combusted instead of when ethane is being formed through a formation reaction. Okay, so make sure you just understand the differences between what you're using to figure out these numbers in Hess's law versus your final answer. Okay, example 2. We're going to calculate the standard or theoretical molar enthalpy of combustion for methanol, and even though it doesn't say it here, they want us to draw a potential energy diagram. Okay, so we're looking for molar enthalpy of combustion for methanol. So step 1, because it's not given to us, we need to write out a balanced chemical equation. So methanol, if you want to look that up, we are going to find it on page 5 right here. Okay, so methanol is CH3OH. And the state of that is liquid. Okay, now since it's a combustion reaction, that tells me that we're going to take our fuel, so methanol, react it with oxygen, and we're going to get carbon dioxide and water vapor. Okay, and now we have to balance here. So we've got one carbon going in, one carbon coming out. We're golden. We have 4 hydrogens going in, so I need to have 4 hydrogens coming out. Okay, and we have 3 oxygens going in, and we have 2 plus, and then we've got another 2 here, so we've got 4 coming out. Okay, so what I need to do is I need to go to my reactant side, and I just need to increase the amount of oxygens that I have going into this reaction. Now, since it's a difference of 1, so an odd number, it doesn't make sense to increase the amount of elemental oxygen. So what I'm going to do is I'm going to increase the amount of methanol I have, which is going to throw everything out of balance here. So I'm going to actually erase this, and we're just going to start over again. So we got 2 carbons going in, 2 coming out. We have, so originally it was 4, but 4 times 2. So we have 8 hydrogens going in. Now we have 8 coming out. And for oxygens now, so we have 2 plus 2. So we got 4 going in. And we have, so we got 4 from here, and we got 4 from water vapor, so we got 8 coming out. Okay, so what I'm going to do is I'm going to ask myself, okay, this 2 times by what will increase this total number to 8. Okay, so if I go 2 times 3, that'll give me 6. 6 plus 2 is going to give me 8. So I'm going to put a 3 for my coefficient for elemental oxygen. And that's balanced. Alright, so I'm going to do the same thing that I did before, which is just list my molar enthalpies of formation. Molar enthalpies of formation, these are in kilojoules per mole. Okay, so methanol. that is negative 239.0. Oh, no, 239.2. Okay, elemental oxygen, elements are always 0. Carbon dioxide, it's right here, so negative 393.5. And then water vapor, so again, remember to be careful about what you select. So water vapor is right here, negative 241.8. All right. So I'm going to write out my formula, and then we'll get rocking and rolling on this. All right, so remember, it's products minus reactants. So I got to start with my products first, the carbon dioxide and water vapor. So we're going to use pink for carbon dioxide. So we have 2 moles of it because that's the coefficient there. And then the molar enthalpy of formation for carbon dioxide is 393.5 plus, so water vapor, I'm going to put that in blue. So we have 4 moles times by negative 241.8. So that's my products taken care of. Now I'll use green for methanol. So subtract, that comes from here. And we got 2 moles of methanol, and it was negative 239.2 kilojoules per mole. Okay. So I've already shown you this calculation just in the previous example here. So that's going to be negative 787, and moles cancels out, so that's just kilojoules. Minus 4 times negative 241.8. It's going to give us negative 967.2. And then we've got 2 times negative 239.2. So that's going to be negative 478.4. kilojoules. All right, so now we're just going to figure out what all this equals. So negative 787 minus 967.2, and then we have another negative times a negative, so that's a positive. 478.4. So our change in enthalpy is going to be negative 1,275.8. Okay, so as a reminder, this is for the whole reaction. Now the question wants us to find the molar enthalpy of combustion for methanol. So we're still following the same two steps that we did for our first example here, except for now we're just going to divide by the moles of methanol here. So again, if you want to call this step 1, and then we can put step 2 here. So the molar enthalpy of combustion for methanol here, so CH3OH, is going to be equal to our change in enthalpy divided by coefficient, which is 2. So that's going to give us negative 637.9 kilojoules per mole. So this is specifically the molar enthalpy of combustion for methanol. All right, so as a potential energy diagram, how we would draw that. So if I look at my change in enthalpy, I'm seeing that it's a negative change in enthalpy. What that means is that my energy term is a product side, because negative means that it's being lost from my system. Okay, so we're thinking, okay, this is an exothermic reaction, and I know that exothermic reactions, what they look like is this. So your reactants have more potential energy than your products. So let's fully label this. So my reactants, I'm going to write out the reactants part of my chemical equation. So we'll see if I can squeeze this in. I might have to make this a little bit smaller here. So we had that plus oxygen Okay, and then for my products, I had 2 carbon dioxides and 4 water vapors. And I'm going to write in my change in enthalpy. So change in enthalpy is going to be that negative 1275.8. I'll have to write kilojoules underneath it. Okay, and then since both my axes are already labeled for me, I'm just going to title this combustion of methanol. Alright, so that would be a fully labeled diagram or potential energy diagram for this reaction. Okay, remember that potential energy diagrams, you use change in enthalpy, you do not use molar enthalpy. Okay, another reason why we know for exothermic reactions that the reactants have more energy, more potential energy than your products is because the only way that this diagram is going to show a negative change in enthalpy, so a loss in potential energy, is if the you start high and you end up going low. Okay, so that is also representing the loss in enthalpy, or the loss in heat. Okay, I've said this before, but just as a reminder, especially when you're picking your molar enthalpies of formation from page 4 and 5 of your data booklet, it's important to pay attention to states. Water for combustion reactions is going to be a gas most of the time. However, it's going to be a liquid if you're talking about either photosynthesis or cellular respiration. Okay, example number 3. Establish the standard enthalpy of formation for carbon disulfide, so CS2, as a liquid, given the enthalpy of combustion for carbon disulfide is negative 1075.1 kilojoules per mole. Carbon disulfide burns in oxygen to produce carbon dioxide gas and sulfur dioxide gas. Okay, so let's start like how I have been starting. So the change in enthalpies of formation, which is in kilojoules per mole. For carbon disulfide, we have no clue what it is. Okay, and actually I'm going to change this to be purple so it's easier to separate this, or tell the difference between what's the question and what I'm writing. Okay, oxygen is going to be 0. Carbon dioxide, we've looked that up a couple of times, so that's negative 393.5. Okay, and then sulfur dioxide, let's look that up. That's going to be right here, so negative 296.8. Alrighty, so let's start out with Hess's law. So products minus reactants. Alright, so pink is for carbon dioxide. Now, our chemical equation's already balanced for us, so that's why I haven't said much about it. So we've got 1 mole times by negative 393 plus, I'm going to use blue for sulfur dioxide. So 2 moles times negative 296.8 minus from the formula. So we've got carbon disulfide. I'm going to use that for green. So we've got 1 mole of it. That looks a little bit like a bracket, so I'm going to go like that. Okay, and I'm just going to put the molar enthalpy of formation for carbon disulfide as X, because we don't know what it is. Alright, and last but not least, we've been given our change in enthalpy, so I got to make sure to write that over here. So that's at negative 1075.1 kilojoules. Okay, so I'm just going to go ahead and cancel out units here. Okay, so multiplying 1 and negative 393.5, that's just going to give me negative 393. So 2 times negative 296.8, that's going to give us negative 593.6 kilojoules. Okay, and then we got minus 1x, which is same thing as just saying x. Alright, so I'm going to first figure out what's inside these brackets before I move on here. Okay, so negative 393.5 subtract 593.6, that's going to give us negative 987.1 kilojoules minus x. Okay, now to isolate x here, okay, I'm thinking to myself, okay, in order to isolate this, I'm going to have to add over 987.1. So that's going to give me negative 88 kilojoules is equal to negative x. And we can divide both sides by negative 1. So we have positive 88 kilojoules is equal to x. So keep in mind that this is our change in molar enthalpy, or this is our molar enthalpy of formation, specifically for carbon disulfide. Okay, moving on to combination problems. So oftentimes you will have to use Hess's law to find the molar enthalpy, and then we got to find something else. Okay, so for our first example here, we have natural gas consists of a mixture of ethane and methane. What mass of water could be warmed from 10 degrees to 60 degrees Celsius from burning 1 kilogram of ethane in a hot water heater? So for this, step 1, we're going to find change in enthalpy using Hess's law, and then we're going to find the molar enthalpy of ethane. Okay, so because we haven't been given multiple equations here, that's how I know that I'm going to use the formula version of Hess's law rather than the additive principle version of Hess's law, where you're given some formulas or you're given some chemical reactions and you need to add them up and cancel out certain species in order to get a net equation. Okay, so let's write out our balanced chemical equation here. So because we have the most information for ethane, and it says that we're burning ethane, so we're going to take ethane, which is C2H6, but just in case you're wondering, like, if you're supposed to memorize that, you don't have to memorize it. You just need to know where to find it. So ethane you can find on page 4. It's right there. So C2H6 gas. Okay, and since we've got that keyword burning, we know it's a combustion reaction. So you take your fuel, which in this case is ethane, react it with oxygen. You're going to get carbon dioxide and water vapor. Okay, let's balance this. We got 2 carbons going in, 2 coming out. We got 6 hydrogens going in. Now we have 6 coming out. We have 2 oxygens going in, and we have 4, and then we have 3, so we've got 7 coming out. Okay, so the easiest way to figure out how to balance this, I just like to go to my reactant side, oxygen, and put it just very briefly as a fraction. Okay, so the 2 just comes from this 2 right here in the denominator, and then what I'm going to put in the numerator is the number of oxygens that we have on the product side. Okay, so now 7 over 2 times by 2, if you multiply that out, right, that's going to give you 14 over 2, which is 7. So right now on my reactant side, I have 7 oxygen. Same with my product side. Okay, but for these types of questions, you don't want fractions for your coefficients. Okay, especially with using Hess's law. If you remember from Chem 20, combustion reactions are the one reaction type that you are allowed to have fractions for your coefficients, but it's just easier to do Hess's law when you don't have fractions for coefficients. So how I'm going to solve this is I'm going to multiply every single chemical species, both on the product side and the reactant side, by 2. So that's going to be 2, 7, 4, and 6. Done. Let's clean that up a bit. All right. So let's do, I'm going to do this in black. So our molar enthalpies of formation in kilojoules per mole. Okay. So for ethane, that's going to be negative 84.0. Elemental oxygen is 0. Carbon dioxide, negative 393.5. Water vapor, so remember that you're looking up water as a gas. So this one that I have underlined right here, negative 241.8. Alright, so that's all my background work. Let's write out my formula. So products minus reactants. Alright, so I'm going to use pink for carbon dioxide. So we have 4 times by negative 393.5 plus, I'm going to use blue for water vapor. So 6. So that's coming from the coefficient there. Negative 241.8. Close the outside bracket. Subtract. So I'm going to use green for ethane. Okay. So 4 times negative 393.5, that's going to give us negative 1574. And then 6 times negative 241.8 is going to give us 1450.8. And these are kilojoules. Okay, and then 2 times 84 is going to give us, or 2 times negative 84 is going to give us, negative 168. Okay, so negative 1,574 minus 1,450.8 plus 168. Let's do that. All right, so now we got negative 2,856.8. Okay, so that was step one. We found our change in enthalpy. Okay, now for step two, we need to find the change in molar enthalpy of combustion of ethane. So find molar enthalpy of combustion of ethane. Okay, and we're going to use our formula. Our molar enthalpy is equal to change in enthalpy divided by our moles, which our moles is going to come from the coefficient of our balanced chemical equation. And that is the moles of ethane. Okay, so I'll do that quickly here. So negative 2856.8 divided by, so our coefficient was 2 for ethane here. Okay, so that's going to give us negative 1428.4 kilojoules per mole. Okay, so now that we have that, remember that's not our final answer. What we're actually looking for is the mass of water. So the reason why we wanted our molar enthalpy of combustion for ethane is because if you remember way back, when we're transferring heat between our system and surroundings, we want to go back to this heat lost is equal to heat gain. Okay, so the left-hand side, that's talking about what's undergoing a chemical reaction. Okay, so that's our potential energy. So what undergoes a chemical reaction is ethane, because that's what's being burned up. So we'll go ethane. Now, you can either just tell combustion reactions, those are exothermic reactions, so that means our negative is going to go on the EP side of our equation. Okay, now for heat gained, we got to ask ourselves, okay, what is gaining heat? Well, from the question, looks like we're only concerned about water gaining heat. So this will be our EK for water. All right. Now, as a reminder of a couple of equations here. So, potential energy, so EP is equal to change in enthalpy, which is equal to moles times your molar enthalpy, which in this case is molar enthalpy of combustion. Okay, and then for EK, that's MC delta T, so mass times specific heat times change in temperature. Okay, so let's expand both of these here. So we got negative moles times molar enthalpy of combustion for ethane. Okay, and actually, let's do all of these as pink so we can color code it so it's easy to track what's happening here, or what belongs to what. Okay, and then EK for water, MC delta T. Okay, so anything that's blue belongs to water, anything that's pink belongs to ethane. So how we're going to rearrange this is, because we're looking for the mass of water, we want to isolate this M. So specific heat capacity and change in temperature, they are multiplying mass, so we need to do the opposite. We need to divide by both of those. So that means we get moles times molar enthalpy of combustion. So we have negative moles times by molar enthalpy of combustion of ethane divided by specific heat capacity of water times by change in temperature of water. So that's going to be equal to mass. So this is going to be the equation that we use. Now, looking at what we have already. So, looks like we've got our change in temperature here. So we got 10 degrees to 60 degrees. So, I think I'm going to have to write this up here because I don't have a whole lot of space. But remember, change in temperature, that's final temperature minus initial. Okay, so we ended up at 60 degrees Celsius. We started at 10. So that's going to be 50 degrees Celsius. Okay, so we've got our change in temperature. Let's just mark that off as, yep, we got it. Okay, what else do we have in the question? So we have a mass of ethane. Now, if I look at what belongs to ethane, so the pink stuff, we got molar enthalpy and moles. Well, we can use mass and molar mass and convert from mass into moles of ethane here. So that's another calculation that I'm going to have to do up here. So remember, moles is equal to mass divided by molar mass. So molar mass you're going to have to figure out by looking at your periodic table. But mass, that's 1 kilogram. Since there's 1,000 grams in a kilogram, mass is 1,000 grams. Okay, we're going to divide that by the molar mass of ethane, which is 30.08 grams per mole. So this is just background work I want to get out of the way. So we got 1,000 divided by 30.08. So it's going to be 33.2446, goes on forever. So remember, I'm going to use this entire raw number that I got in my calculator, but I'm just writing ... to mean number keeps on going on forever, but I'm not going to write it all. Okay. So we have our moles. We already found out our molar enthalpy of combustion for ethane, and we can look up the specific heat capacity of water if you haven't memorized it already. Okay, so let's get going on this. So we've got negative, so our moles, that was that 33.2446, goes on forever, moles. Okay, our molar enthalpy of combustion, that was this number right here. Okay, specific heat capacity of water, that we can find on page 3. So, right here. So 4.19 joules per gram degrees Celsius. Okay, and then the change in temperature we figured out was 50 degrees Celsius. Okay. So keep in mind here, if you were wondering about this change in temperature, where I just wrote 60 and 10, and I didn't write 60.0 and 10.0, keep in mind I'm not worried about sig digs for this answer of 50 degrees Celsius because it's not a final answer. Okay, so let's look at my units here. So moles cancels out, degrees Celsius cancels out, but I'm noticing we got joules versus kilojoules. Okay, so the easiest way to kind of adjust things is to go kilojoules over kilograms. Okay, so this number is still going to be the same because kilo in the numerator and denominator, they cancel out, so it's not going to change this number right here. Okay, so now our kilojoules are going to cancel out, and we are going to go equal to mass. Okay, so this is the mass of water. So let's put this in our calculator. So negative answer, so we get that 33.2446 goes on forever, times by negative 1428.4, close that bracket, divide by bracket, 4.19 times by 50, close the bracket, enter. Okay, so we get 226.6668. And our units are going to be kilograms because that's the only thing that didn't cancel out. All right, now looking at our question, the numbers given to us, all of them were in 3 sig digs, so my final answer needs to be in 3 sig digs. So that means my cutoff line is going to be right here. So that's going to turn my answer into 227 kilograms. All right, moving on. So example 2, what mass of water could be heated from 20 degrees to 55 degrees Celsius by burning 6 grams of propane? Okay, so this question, very similar to example 1 here. So we're still going to do step 1, find change in enthalpy using Hess's law. Step 2, figure out your molar enthalpy. And then I'm just going to write in here, this is step 3. So step 3, you do your EP is equal to EK, and you figure out your energy transfer formula, and you isolate whatever you need to isolate. So in this case, we're going to need to isolate mass because we're looking for mass of water. So if you want, you can pause the video and work it out for yourself. I will go ahead and write out my solution here. So first things first, we're going to write out balanced chemical equation. And what's happening here is we are burning propane. So propane, if you don't know the chemical formula of that, you can find that on page 5 right here. So C3H8 as a gas. So for combustion reactions, your products are always going to be carbon dioxide and water vapor. Oh, I'm going to go ahead and balance this. Remember, for combustion reactions, you always balance it carbon first, then hydrogen, then oxygen. So molar enthalpy of formation for propane, it's negative 103.8. Oxygen's an element, so it's 0. Negative 393.5. Negative 241.8. Products minus reactants. Okay, so now that we have change in enthalpy, now I need to find change in molar enthalpy. So we're finding the change in molar enthalpy for the combustion of propane. So propane just has a coefficient of 1. Alright, so looking at how my previous calculation went, I know I need to first find the change in temperature as well as moles of propane. So this is change in temperature of the water. So remember, it's final minus initial. So moles of propane is going to be equal to mass of propane divided by molar mass. So since this is another combustion reaction, the negative is going to go on my potential energy side, which belongs to propane, because propane is what's undergoing a chemical reaction. And water is what is going to be gaining heat. But since water isn't undergoing a chemical reaction, that's why it's a EK term, or a kinetic energy term. Alright, so our mass is equal to 1.8957. Goes on forever, and our units are in kilograms. Let's look at our numbers given to us. Looks like they're all in 3 sigdigs. So that's what my final answer should be in. So 3 sigdigs, my cutoff line. Let's do a different color here. And there you have it.